Okay, so our next speaker is Anna Parraga, who's coming to us from Argonne National Lab. And she's going to talk to us about some of the integration with the Advanced Photon Source and some of those software ecosystem issues.
Great, thank you so much. So I am coming from the Advanced Photon Source, and today I would like to share for you my perspective on some ways that we can work towards improving our current software ecosystem to better support our user facilities. And I don't think that I need to convince you. I think we all have this idea in our minds of the benefits that come when we can connect our instrument data and connect our scientific research facilities to these big scale computing facilities and provide more computational power across sites. And I think there's a lot of momentum for this currently. There are a lot of national initiatives coming out that we are hearing about to support this. So programs like IRI, American Science Cloud, ModCon, we have a lot of momentum right now to drive this work forward. And we also have a strong foundation that we are building upon. So we are at least able to share data securely with our users. We're able to allow them to do some processing. And also we're providing some foundational tools to support our users across the data lifecycle. We are integrating our control system in with our data management system, as well as the collaborations that we've been forming between light sources and computing facilities already. So these partnerships have allowed us to have queues for on-demand computing for our experiments. They've provided us with dedicated allocations for our facility. We have service accounts specific for our different beamlines, and also we have ability to provide compute with these Globus endpoints. However, there is still a lot of work that needs to be done and a long way to go before we fully close this loop between our data generation and our compute in a way that is actually able to provide streamlined experiment steering. And so I'd like to highlight today a few forward-looking opportunities. I think there are a lot of different improvements that need to be made, but I've picked 3 today so far. And I'll start by outlining what I think the challenges are. And then I'll go through and say what I think needs to be done in order to address these challenges. And then I'll provide a few examples of work that's been started for different projects moving in the right direction. So the first of these forward-looking opportunities that I'd like to discuss is cross-facility awareness. So right now, we do have the ability to process our APS data either locally or at the different supercomputing facilities. However, the way that the users are interacting with our system is we're providing a workflow to them, and one of the arguments to this workflow is the machine that they want to run on. However, most of our users don't know anything about these computing facilities, and they really have no intelligent way of making this decision themselves. So we're providing to them this decision of where to run, but they have no idea which of these facilities will really return the answer to them most quickly. And I don't think they really should have to make that decision themselves. So what do we need to actually address this issue? So it would be great if there was some sort of way to automate this decision, if there was some way to select the best site based on information. And the users shouldn't need to have to choose their compute site manually. So what would be great is if we had some sort of common API from the facilities, which could provide us at least some sort of estimate about how long it might take before we can get compute and how long it might take to get our answer back. And then we could use our data management system to query those APIs and make a decision about where we should route this job. It would be really awesome if there was some kind of way that we just had a common interface and it would route the job for us, but understandably, these systems are all built for different purposes. They have different scheduling systems, so I don't think that's very likely, but at least do have more information about where these jobs should go. And we heard earlier about this IRI interfaces Pathfinder collaboration, which is all of these computing facilities working together to provide these sort of common APIs for their users. So far they have provided in recently these facility status APIs. So basically these initial API endpoints will report on information about, is the machine actually available? Is there going to be some sort of maintenance or downtime? And this at least is a first step to allow us to say, well, we're not going to submit to a machine that we know is not even online. So that at least allows us one step towards providing information to users about where should we run our jobs. So the next topic that I'd like to discuss is how do we improve our data streaming infrastructure? So far we've demonstrated streaming to different HPC resources, but it hasn't yet been used in our live experiments at the Advanced Photon Source. And I think if we really want to do true experiment steering, we need to skip past the file I/O that is slowing us down. We want to provide files to users to take home with them, to do some sort of reprocessing of data. But if they just want to get a look about what am I doing right now, what am I seeing, am I really processing the right data, is my experiment going well, then having files is really just slowing us down. However, if we want to actually use the streaming solutions that we have currently, there is a lot of manual setup that needs to happen first. We need to have compute nodes already up and running with the streaming consumers ready to accept those data streams before the data starts flowing. So this means that we're making a reservation, which might be sitting idle for a long time. You know, this experiment is very stop and go. We might be sorting out our alignment first before we even get to the computing. So really it's wasting a lot of the reservation already. Also, we have to convince the computing facility to allow us to stream into their compute nodes. They're not just going to blindly allow open incoming network connections. There also is no standard interface across the facilities, so we need to have somebody who knows how to connect and get compute nodes at each of them. And then this is not something that the Beamline staff themselves would ever really be able to manage. We need to take these sorts of computing setup out of their hands. However, as a data management team, we're not going to be able to support hundreds of experiments all going on at many different beamlines if we need to do this sort of setup for each of these experiments. So really right now it is too cumbersome. So what do we need? We need to be able to establish these network connections when the data is ready. When the experiment actually starts producing data, that's when we need to hook into the compute nodes, no sooner and no later. We also need to be able to balance our loads across different compute nodes. So we need to be able to not just be hitting one streaming consumer on a single node, but also be able to distribute it across multiple nodes. And if the message is not received, if something is lost during transmission, we need to be able to resend that information and recover from those failures. It would also be great if we could do this consistently across sites so that we can pivot between sites as we need to use different ones. And at the moment, we don't really have a way of bringing the answer back. So we might be able to stream out to an HPC facility, but then how do we actually stream that data back to the APS and display it to a user in a very nice way? Right now, we don't have any visualization tools that are capable of ingesting streams of data. So there has been a lot of foundational work for this very recently in this year. So we heard a little bit about the LCLS stream, which has been demonstrated to submit to Frontier. Also, the ESNet is looking to provide their own EdgeFAT solution to improve streaming infrastructure from instruments to HPC facilities. We have at the APS, we have the PBA-Pi streaming framework, and this is meant to create streams of EPIX data, which is the format from our X-ray instruments. Also, the Secure Scientific Service Mesh has been developed at the OLCF, and this should allow streaming to RabbitMQ or Redis. And then we do rely on a lot of Globus tools currently at the APS, and they are looking to release a streaming solution as well later this year. The last topic that I'd like to bring up, which is one that I think is often overlooked, is actually uplifting the community software that we rely on. So at the APS, we have dozens of different beamlines, and they are all doing different types of X-ray science. But there are some existing community softwares that they use to process this data. So these are packages that were often developed out of the X-ray community, and the users and the staff are already familiar about how to run these software. However, most of the existing software that these beamlines rely on was not developed to run at an HPC center. It is not running in a distributed fashion. It might not even be using GPUs. And it's really meant for just the user who's bringing their laptop or the workstation that is sitting at the beamline. So although we can build all these really nice fancy pipelines, if we're just throwing this unoptimized code at a supercomputer, we're really not taking advantage of that resource or even really speeding up our processing. So what do we need? In this modern IRI ecosystem, we need our analysis software to be capable of processing data streams if we are streaming. We need to be able to efficiently use multiple nodes and GPUs. And it would be great if we could deploy our software in standardized containers so that we can fit more easily between facilities and not care about where we're running. So what this means is that the maintainers of those community software packages, they need to be connected with the experts of these other software ecosystem tools that we are building. So we should be connecting them with container experts. We should be connecting them with HPC experts, and we should also be connecting them with the developers of our streaming frameworks. As far as the projects that have started in this space, there are certainly a few different software that we use at the APS where we are moving in this direction. So we do have a containers working group, which we just started at the APS level. Then we've also had a few different of our software packages develop streaming solutions and also making better use of the ALCF and Polaris. But I also want to share from my own personal perspective, maintaining our allocations at the computing centers, that these folks are really willing and able to help you. So if you have some sort of code that you want to optimize to run on their facilities, there are many experts there who want to engage with you and make them better. So I think we really just need to make those connections between the maintainers of our software and the maintainers of our facilities. So as a conclusion, I would just like to reiterate that there is a lot of really great work that we need to do. There's a lot left still to do to improve the software ecosystems that we have at our user facilities. So let's get to work.
Have any questions?
Okay, so great presentation. I just want to bring up a question about how, as a community of IRI, trying to maintain and also creating new direction of ecosystem. The reason I'm asking this is, in the past, especially during the ECP, exascale computing project, still Python was not regarded as a first citizen in the entire software ecosystem. However, in the era of AI, machine learning, and IRI, definitely I have seen lots of Python software in the presentation. So basically my question is, you already mentioned some capability or maybe some community support from HPC is missing. So do you also want to, conventional HPC people to step even further to assist the users in IRI, or should we also consider Python-based conventional HPC solution? So which one do you prefer?
The more tools and the more support that we can get from facilities, the better. Because, some of the maintainers of these scientific software packages are also beamline scientists that are splitting their time to be able to, develop these softwares as well as run a beamline. So if you can make it easier for them by meeting them where they are, if their tool is written in Python and you have support to optimize that Python, I say absolutely. That doesn't mean that every code will be written in Python, and some softwares are really going to get those power users that want to dig very deep. But I think more is better.
Maybe a couple questions or maybe a couple comments. So each facility, each computing facility is heterogeneous with respect to their software stack, but also their hardware stack. So do we want to head more towards, within a given workflow, heterogeneous tasks that are targeted specifically to a given architecture, where they'll run at one facility? Or do we want portability tasks that are portable and can run on any facility? If we want that option, where does the funding for that come from? Is it the experiment themselves that needs to supply the funding for the user facilities to actually do that porting? Does the facility itself provide some funding for that? What's the practical, how do we do this practically?
So you're talking about funding for uplifting software and data ecosystem?
Sure. I can see, I'm not a domain scientist, but I can imagine a domain scientist goes through and they have some new experiment they want to run, and they write a kernel, say for a given GPU architecture, and they've blown through their budget, just getting that working. But now a new system comes online and it's out of date, their kernel's out of date, or they want to run and expose themselves to different facilities. How do we support that? They don't have the money to do that anymore, to hire the developers to do that. Is it the facilities that need to do that? Is it they need to just build that into their budgets? I don't know. What do you think's the right way that we should go about that?
I think as much as a facility as we can provide those tools to them, I think the better. So this is where we're trying to make sort of canned workflows. If there is some sort of data processing that we know that users are commonly going to do, if there's some sort of, first solution, maybe they're going to want to do some sort of post-processing after that and refine the answer even further. But if there are some sort of standard tasks that we know that we're going to be doing, that would be a great way where we can already provide those tools to them so that they don't have to write their custom kernel, so they don't have to maintain these softwares. And I think where that can be built into the facility operation budget, that's better. I know that's how my team personally on the software side is funded. So I think that facilities do think about at least providing some computing support, and the more that they can do that, the better.
A naive outsider question. I've heard Slurm mentioned a couple times. You also had containers and Kubernetes on there. Is there a predominant scheduler amongst all the different resources, like a preferred one? Is there a trend that the labs are moving towards, Slurm versus Kubernetes?
Sure. So I think that the NERSC and the OLCF are both running Slurm, and the ALCF is running PBS, and I think also for our local APS cluster, we're also running PBS. So I would say that those are the main two that people use.